Hello everyone. In the last session, we discussed BH curve or hysteresis loop for any magnetic material. Now in today's session, we will discuss construction and working principle of transformer. The transformer is a static machine. A transformer is a device, a passive device that transfers electrical energy from one circuit to the another circuit by means of electromagnetic induction. So the working principle of transformer is Faraday's law, Faraday's law of electromagnetic induction. But this electromagnetic induction is mutual induction. What is mutual induction? The mutual induction is when the two coils are magnetically or inductively coupled or connected, and if the current in one coil changes, then the EMF is induced in the another coil. That means these two coils are electrically isolated. For example, there is a coil 1 and here there is a coil 2. So if we connect a source here and we connect load here, these two coils are electrically isolated or separated. That means when current flows through the primary winding, this is the primary winding which is connected across source, and uh, this is primary winding, this is secondary winding. Secondary winding is connected across load. Load can be anything. It may be resistance or any device like motor, lamp, or any other electrical equipment. So the two coils are electrically isolated or separated because the current of coil 1 cannot flow to the coil 2, and in between coil 1 and 2 or coil primary and secondary there is an insulation. So electrically they are isolated, but magnetically or inductively these two coils are coupled or connected. That means when current flows through the primary winding, here flux is generated, and this flux can link with the secondary winding also, because the magnetic flux has no insulation or no insulator. Magnetic flux can flow through air also. It can flow through any good magnetic material which is called core. So the two coils, primary and secondary, they are electrically isolated and magnetically coupled. This is a schematic diagram of a transformer. We can observe here a magnetic core. So this part is magnetic core. On right hand side there is a blue winding which is primary winding, and it is connected with the AC supply. The red winding is the secondary winding and it is connected with load. So you can see both the coils are apart from each other, electrically isolated, but they are provided on a common magnetic core. So when we switch on the supply, the current I will start to flow through the primary winding, and this part will work as an electromagnet. Whenever current flows through any electromagnet, it will produce a magnetic flux. The core, magnetic core, will provide a low reluctance path to this magnetic flux, let's say 5 Weber. So this 5 Weber magnetic flux, it will flow through the core, and in this turn the magnetic flux will link with the secondary winding here. And as per the Faraday's first law, whenever there is a change in magnetic flux linkage with any coil or conductor, an EMF is induced in it. So in the secondary winding, EMF is induced, and this EMF will push the current I through the secondary winding. So this is I1 and this current is I2, and the lamp will glow. Or any load, if we connect across the secondary winding, we can operate the load. So this is nothing but mutually induced EMF. Change in current in one coil will induce the current in second coil, mutually induce EMF. And by doing so, the electrical energy from primary is transferred to the secondary winding without any electrical connection between the two coils. Let's see the working principle of a transformer. In the diagram, we can observe there are two coils, coil A and coil B. Both are wound over the core. The coil A has N1 turns, coil B has N2 turns. Coil A is connected with a DC source or battery with the help of switch in series with a variable resistor, and coil B is connected across a galvanometer. These two coils are kept near to each other, and when we close the switch here, current I starts to flow through the coil A. It will produce the magnetic flux, and this magnetic flux links with the N2 number of turns of coil B, and as a result in coil B EMF is induced. As this circuit is complete, it is a closed path. This induced EMF in coil B will force the current to flow through it, and this current will be sensed or detected with the help of deflection of galvanometer. Now the source is DC, and we know that DC does not change its direction or magnitude. As a result, whatever flux, magnetic flux produced by coil A will also steady or constant. It will not change the magnitude or direction with respect to time, because flux depends on current. As a result, there is a constant or continuous flux, and EMF is induced in coil B only during switching instant. That means when we close the switch, magnetic flux becomes maximum from 0, and flux linkage with the coil B becomes maximum from 0. So it is change in magnetic flux. So at that time EMF is induced. Now if we keep the switch closed, the flux remains constant, flux linkage remains constant, and as a result no EMF will be induced, because as per Faraday's law, EMF will be induced in the coil only when there is a change in magnetic flux linkage. Now when we open the switch, the current in coil A becomes 0 from maximum, flux produced by coil A becomes 0 from maximum, and flux linkage with the coil B also becomes 0 from maximum. So this is change in magnetic flux. Earlier magnetic flux linkage was maximum, now magnetic flux is 0. So again EMF is induced. So if the source is DC, there will be induced EMF in coil B only during switching instant. Only during switching instant. That means when we close the switch, EMF is induced. When we open the switch, EMF is induced. Remaining at all instants, EMF will not be induced because flux linkage remains constant. And due to this reason, a DC transformer is not possible. DC transformer is not possible because when the source is DC, induced flux produced by the primary is steady or constant. So what to do to have a continuous change in magnetic flux linkage? In place of DC source, we can connect alternate. So in this diagram, two windings, primary and secondary. Primary is connected with AC power source, which is having sinusoidal current or voltage, and the coil B is connected across the lamp. So when this AC flows through the primary winding, alternating current flows through the primary winding, it will produce continuously changing magnetic flux, because at each instant the magnitude of current is changing with respect to time. As a result, flux is also alternating in nature. And due to that, the flux linkage with the secondary winding is also continuously changing. And as per Faraday's law, whenever there is a change in magnetic flux linkage, an EMF is induced in it. So due to this continuously varying field, due to the continuously varying magnetic flux linkage, EMF is induced continuously in secondary winding. So this is the working principle of transformer, mutually induced EMF. Now let's see the construction of a single phase transformer. Mainly there are two types of transformers based on power supply, single phase and three phase. So first we will discuss single phase transformer. The transformer consists of mainly two components, two parts. One is called core, magnetic core, and the second is windings or coils, primary winding and secondary winding. Now this core or magnetic core is a part of a magnetic circuit on which the windings or coils are placed. In short, core is a component of the transformer which is used to provide support to the coils or windings. And some other important components or parts of the transformer are transformer tank, oil and oil tank, insulating materials, bushings, breather, cooling system, protective devices, and some other auxiliary equipment. Let's see magnetic core in a little bit detail. As I said earlier, the magnetic core provides a low reluctance path to magnetic flux. So when we apply the current to primary, flux is produced and core will provide a low reluctance path to the magnetic flux from primary to secondary so that maximum flux linkage can occur, and a mechanical support to the winding. So the core provides mechanical support to the winding. The core of the transformer is either square or rectangular type. Rectangular type. So it depends on design of the transformer, whether it may be square shape or rectangular shape. This core is made up of any good magnetic material like silicon steel or sheet steel laminations, which are assembled to provide a continuous magnetic path for the magnetic flux. And the thickness of these laminated sheets of steel are 0.35 to 5 millimeter, and they are insulated with a varnish. Varnish is a liquid insulation or oxide or phosphate, and then form as a core. So single lamination is very thin and it is having a thickness of 0.35 to 5 millimeter. In order to have a core of particular dimension, a number of laminations are together, assembled together. All the laminations are insulated from each. So here you can see core, magnetic core. Red is the primary winding and blue is the secondary winding. We can see from the diagram that let's say N1 is primary turns and N2 is secondary turn. We can observe that N1 is greater than N2. Number of turns in primary is greater than number of turns of secondary. So we can also denote as NP or NS. So here NP is greater than NS. In a few transformers, it could be reverse, like NP may be less than NS. And what is the significance of this relation that we will discuss later? Based on number of turns in primary and secondary winding, the function of the transformer is decided, whether it is step up transformer or down transformer. If we talk about the magnetic core, then the question is why laminated core is used and why not a solid core? The reason is very simple. To understand this question, observe the two diagrams. Let's say this is diagram number 1 and this is number 2. In diagram 1, the core is solid. As a result, it is having a larger area. And when current flows through the primary winding, it generates the magnetic flux. This flux flows through the core and links with the secondary winding. Now, in this case, in this process, core also links with the core flux will also link with the core also, same as secondary winding. For example, let's try to understand with simple diagram. This is primary, this is secondary and core. When we apply the current in the primary, flux is generated here. This flux flows through the core and it links with the secondary winding. During this process, the magnetic flux also links with the core itself. Now remember, core is a magnetic material and magnetic material is also a conducting material or a conductor. So flux links with the core material, and as per Faraday's first law, whenever there is a change in magnetic flux linkage with any conductor or coil, EMF is induced in it. So along with secondary winding, EMF is also induced in the core because flux linkage occurs with the core also. And if the core is made up of solid design, solid core is used, then its area is larger. If the area is larger, flux linkage is more and more EMF is induced. Due to this more EMF, more current will flow through the core or more current is induced in the core. And as a result, in the core, there will be I square RT losses. These I square RT losses are nothing but heat. So the temperature of the core increases. One more thing, if the area is more, resistance will be less. And if the resistance is less, more amount of AD current is produced. So whatever current induces in the core is known as AD current. And this AD current generates heat and power loss in the core. And these losses are known as AD current losses. Remember one more loss we discussed in the last session, hysteresis loss. Hysteresis loss occurs in magnetic material, that is core. So along with hysteresis loss, AD current loss occurs. Now if the core is laminated, that means core is divided into very thin laminations and each lamination is insulated from each other. So in this case you can observe each lamination has very small area. As the area is small, its resistance is high, and due to increased resistance in each single lamination, very small amount of AD current is generated, and due to this small amount of AD current, heat produced and power loss caused by the AD current is very less. So to reduce the AD current loss, to reduce the temperature rise of the core is always laminated. What core, and you can see here, these are the core laminations. So here there are two types of laminations shown. One is E shape and another is I shape, and it is very thin. Number of these type of laminations are taken together, assembled together, and a solid core is prepared. So laminations are arranged to form a core of a transformer. There are laminations also. You can see here first one is E and I type. Second one is EE type laminations. Third one is LL type laminations. And fourth one is U and I type lamination. So depending upon the design, depending upon the manufacturing requirement, different types of laminations are used. And you can see here many numbers of E and I type laminations are taken together, they are assembled together, and we will have a thick core. But remember, each lamination is insulated from each other. So there is an insulation between two consecutive lamination. So electrically, these laminations are isolated, magnetically, they are connected. A few other examples are shown, U type and I type. So this is magnetic core or magnetic core. Here a photo shows the manufacturing of core or assembling of the core with the help of number of laminations. Then comes windings. Once the core is prepared, primary and secondary windings are placed on the core. So there are two or more windings which are electrically isolated but magnetically coupled. The winding which is connected to the AC main supply is called a primary winding, and the winding which is connected to the load is known as secondary winding. These windings are electrically isolated from core. That means there is an insulation between winding and core, and also electrically isolated from each other. These windings are made up of good conducting materials like high grade copper. So mostly copper is used to prepare the primary and secondary winding. When the primary winding is energized with alternating voltage source, that means when alternating current flows through the primary winding, an alternating magnetic flux is produced in the transformer, and this magnetic flux depends on the magnitude or amplitude of the magnetic flux depends on the applied voltage magnitude, frequency of the supply, and the number of turns on primary side. This flux links with the secondary, and as for mutually induced EMF is induced in the another winding, that is secondary winding, and this EMF is called mutually induced EMF, and the phenomena is called mutual induction between two coils. Now the output voltage in the secondary winding, it depends on three parameters. First, number of turns on the secondary winding, amount of magnetic flux linking with the secondary winding, and frequency of the supply which is provided to primary winding. So you can see the effect of number of turns. The primary is constant. If number of turns are increased, the output is increased. That means if NP is less than NS, number of turns in secondary winding is greater than number of turns of primary winding, then more EMF is induced in primary winding. But if NP is greater than NS, then less EMF is induced in primary winding, in secondary winding. Input to the primary winding is constant. So if we increase the number of turns in secondary, more EMF is induced. If we decrease the number of turns in secondary, less induced. This is schematic of transformer construction: core, NP, NS, primary voltage and secondary voltage. And these two are the symbols of transformer. This is what I said earlier. If secondary voltage is more than primary voltage, that is if Vs is greater than Vp, then the transformer is called step up transformer. So in this case, NS is greater than NP. Number of turns in secondary is greater than number of turns in primary. Reverse is the case. If secondary voltage Vs is less than primary voltage Vp, that is Vs is less than Vp, then the transformer is called step down transformer. And in step down transformer, Ns is less than Np. That means number of turns in primary is greater than number of turns in secondary. So both the transformers are shown here. Np and Ns. Obviously Np is greater than Ns or Ns is less than Np. So it is step down transformer. And in this case, number of turns of primary is less than number of turns of secondary. So it is step up transformer. These windings are also called HV and LV winding. HV means high voltage winding and LV means low voltage winding based on the voltage level. Compared to LV winding, the HV winding needs more insulation because it has to withstand high voltages. So the thickness of the insulation in HV winding is more than the thickness of LV winding. So here you can see it is a magnetic core and two windings placed on core. Now EMF induced in single phase transformer. So we can derive the expression or equation of EMF induced in secondary winding. To understand this, let's assume N1 is number of turns in primary, N2 number of turns in secondary, phi m is maximum flux in the core in Weber, which is also given by Bm into A, where Bm is magnetic flux density. We know that magnetic flux density Bm is equal to maximum flux upon area. F is the frequency of AC supply in primary. In the transformer, source of AC is connected to the primary, and whatever current flows through the primary winding is called a magnetizing current. Magnetizing current because it produces magnetic flux. This flux link with the secondary and EMF is induced in the secondary. So the nature of the flux is same as nature of the current. As the current is alternating in nature, flux is also alternating in nature. And it is having the same frequency, flux is having the same frequency as current. So we can observe phi m is the maximum flux and T by 4 is time period at which or instant at which flux becomes maximum. Now this flux rises sinusoidally to its maximum value phi m from 0, and to become maximum it takes T by 4 second, where T is the time period. Time period is what? Time required to complete one cycle, and its value is given as 1 upon F. F is the frequency. So in T by 4 second, flux becomes maximum from 0, and therefore the average rate of change of flux is given as phi m upon time. So phi m upon T by 4. In place of T we can put 1 upon F. So this equation becomes phi m upon 1 divided by 4F. We can rearrange the equation 1 and we will have average rate of change of flux is equal to this 4F will be at upside, so 4F phi m Weber per second. This is average rate of change of flux with secondary 4F phi m. The induced EMF per turn, if there is single turn, then the induced EMF per turn is nothing but rate of change of flux linkage per turn. That means induced EMF is equal to 4f5m volts. The form factor for sinusoidal alternating waveform is the ratio of RMS value to average value, and its value is 1.11 for sinusoidal waveform. So the RMS value of induced EMF per turn is form factor multiplied by average EMF per turn. So the value of form factor is 1.11 multiplied by average EMF per turn is 4f5m volts. So 1.11 into 4f5m volts. And as a result, if we simplify, we will get the EMF induced per turn. Now, RMS value of induced EMF in whole primary winding EP is RMS EMF per turn into number of turns in primary winding. We can put the above relations here. So EP is equal to 4.44 F 5M into N1. N1 is the number of turns in primary winding. And similarly, the RMS value of induced EMF in secondary winding ES, in place of N1 now we have to put N2 because number of turns of secondary winding is N2. So 4.44 F N2 5M volts. So from equations 3 and 4 we can take a ratio Np upon Ns is equal to N1 upon N2. So by arranging this Np upon Ns, Ep upon Es is equal to N1 upon N2. We can arrange Ep upon N1 is equal to Es upon N2. So divide Ep by N1 and divide Es by N2. We will get 4.44 F5M. 4.44 Fm. As derived above, this Ep upon Es is equal to N1 upon N2 is equal to K. This is nothing but a ratio of primary turns to secondary turns, N1 upon N2, or the ratio of primary winding induced EMF to secondary winding induced EMF, EP upon ES, primary voltage to secondary voltage. This ratio is called voltage transformation ratio. Voltage transformation ratio. And K is also known as turns ratio. If you take N1 upon N2, then it is turns ratio. And if you take EP upon ES, then it is known as voltage transformation ratio. So if N2 is greater than N1, step up transformer, otherwise it is step down. So two transformers are shown here, step up transformer and step down transformer. Various values are given, so just go through the PPT provided and compare the number of turns and the parameters change from primary to secondary. If you compare these two diagrams, the parameters that remain unchanged from primary to secondary are power and frequency. So the frequency of voltage at primary side is 50 Hertz. At secondary also it is 50 Hertz. Total power at primary is 2000 watt. On secondary it is 2000 watt. So these two power and frequency remain constant or unchanged in primary and secondary winding. The parameters that change from primary to secondary are voltage and current. So here 1000 volt at primary, 200 volt at secondary. Current is 2 ampere in primary, in secondary current is 10 ampere, and this is true for both, whether it is step up or step transformer. Now apart from single phase and three phase transformers, there are two other types of transformer. Based on arrangement of windings and core, how the windings and core are arranged, the transformer is classified as core type transformer and cell type transformer. So here core type transformer. What is core type transformer? The winding surround the core, primary and secondary winding, they surround the core. And in cell type transformer, core surrounds the winding. So let's see the diagram. You can see in the core type transformer here, core is provided, and on this side there is a primary winding, here there is a secondary winding. So you can observe windings windings are provided in a such a way that they surround the core. Core is in between two windings. And in cell type transformer, there are three limbs of the core. Limb 1, this is second, and this is third. And primary secondary windings are provided on middle limb, limb number 2. So here core is outer side at both the ends and windings are at the middle. So core surround the transformer winding in cell type transformer. In core type transformer, reverse, winding surround the core. So depending upon the requirement, core type and cell type are used. So you can see here another diagram for core type transformer. There is a magnetic core, and around the core two windings are kept or placed. So core type transformer, here in cell type transformer, outside there are core and in the middle limb winding is provided. So winding is surrounded by core limbs. On a common limb in cell type transformer, primary and secondary winding provided. So this is schematic, another schematic diagram, HV and LV windings and magnetic core. So core type and cell type transformer. There is a comparison between core type and cell type transformer. Definition: the windings surround the core. In cell type, core surround the winding. Lamination shape: the lamination is cut in the form of L strip. So here two L strip are joined together to prepare the core. Here laminations are cut in the form of long strip of E and I. E and I. So this type of laminations are there. E and I. Cross section. Cross section may be square. In core type transformer, in most of the cases it is square or cruciform and three stepped. In cell type, cross section is rectangular in shape. So when you join this, it is a rectangle. Copper requirement is more. For core type transformer, more copper is required. In cell type transformer, less copper is required because the distance between two coils is less. So flux linkage occurs very easily. Here in the core type transformer, distance between two coils is more. So we need to produce more amount of flux. There are other names of these two transformer. Core type is also known as concentric winding or cylindrical winding transformer. And cell type transformer is known as either sandwich or disc winding transformer. Sandwich winding or disc winding transformer. Number of limbs 2. So this is limb number 1, this is limb number 2. In cell type there are 3 limbs, 1, 2 and 3. Insulation requirement is more in core type transformer. Insulation requirement is less in flux is equally distributed on the side limb of the core. Here central limb carry the total flux and side limbs carry half of the flux. Winding as shown in the diagram earlier, The primary and secondary windings are placed on the side limbs. Here both the windings are placed on central limb or middle limb. In core type transformer there are two magnetic circuits. In cell type only one magnetic circuit. Losses, core type transformer has more losses, cell type less losses. Maintenance is very easy in core type because both the windings are easily accessible. In cell type transformer, maintenance is difficult because windings are provided on central limb. So windings are not easily accessible. Mechanical strength is low in core type transformer. In cell type transformer, it is very high. Output power is less in core type. In cell type, it is high. Natural cooling does not exist. In cell type transformer, natural cooling exists. So this is all about a single phase transformer. There is three phase transformer. So I am discussing quickly that three phase transformer, most of the power system is three phase in nature, and three phase circuits are most economical for AC power transmission and distribution. As a result, three phase transformers are widely used in place of single phase transformer. So three phase transformer it may be a single unit. So there are three single phase transformers and they are connected in three phase, or there is a single unit. So all the windings, all the three phase windings wound around the same core and immersed in oil tank. So in practice, the choice between these two, whether a single unit or made up of three single phase separate units connected in star or delta, it depends on one or another type of applications like economical reasons, transportation, future expansion, reliability, cost, etc. For a same kVA rating, if we compare a single three-phase transformer, it is cheaper, smaller, lighter in weight and compact as compared with three single-phase transformers connected as a three-phase mode. And in the case of three single-phase transformers connected in three-phase mode, more copper and iron materials are used. So it is costlier. Moreover, this arrangement occupies more space. So it is better to construct a single piece three-phase transformer in place of connecting three single-phase transformers in. So here construction is shown. You can see three phases. This is phase A, phase B and phase C. Core type transformer, and cell type transformer, phase A, phase B, phase C. So this is three phase five leg core. There are five limbs or legs, and in core type there are three legs. So three phase three leg transformer. Here three single phase transformers. This is transformer number 1, transformer number 2 and transformer number 3. These three transformers are connected to have three phase transformer. This is core transformer schematic arrangement. Primary and secondary windings are provided on each lead. This is also three phase transformer LV winding, their respective insulation, HV winding and HV insulations are shown in the. So if we have three single phase single phase transformers, and we would like to operate these three single phase transformer as one three phase transformers. Then we can connect these three transformers in different manner. It could be star-star connection. So primary is connected in star, secondary is also connected in star. Then delta-delta. So primary, secondary both are connected in delta. Star-delta, delta-star, open delta, which is called VV connection, and Scott connection TT. So these two are special applications of transformers, open delta and Scott. So this diagram, different components are shown. First one is transformer tank, main tank. This is the main tank. Second one is HV bushing, high voltage bushing. Third one is LV bushing. So this is HV bushing. The smaller ones are LV bushing, low voltage bushing. Fourth is radiator. This is radiator for cooling purpose. Fifth is cooling fan. So here cooling fan is provided. Sixth is conservator tank. This is oil tank and known as the conservator tank. Seven is ground terminal. This is ground terminal. Eight is drain valve to filter out the oil. Nine is breather. Breather is used to absorb the moisture from oil. And 10 is oil temperature or pressure gauge, which will measure and display oil temperature and pressure inside the transformer tank. 11 is current transformer bushing to measure the current, and 12 is the control panel. These are the different types of different components of the transformer. This is very first transformer which was designed by William Stanley in 1885. And Stanley's first transformer, which was used in electrification of Great Barrington, Massachusetts in USA in 1886. So these two are the transformers first time designed by William Stanley. This is inside view of three-phase transformer during construction. We can observe various components, core, winding, and some other auxiliary components. The transformer placed in substation. We can see the size of the transformer, various parts like bushing, radiators, control panel, etc. Here also another transformer in substation. This RYB, this is red phase, this is Y phase and B phase. They are the three phase system. Photographs of a transformer. We can observe the size of the transformer and compare with it human being. Very large, very giant transformer. So in the next session, we will discuss rotating machine.